Spectral imaging and also remote sensing and horizontal microscopy with lasers. So, for the network, briefly, it has been created here in Senegal in '91. So next year it will be we will celebrate the 30th of this network, and it was with a strong support of Professor Abdou Salam, who is a Nobel Prize of Physics. He was the director of the International Center for Theoretical Physics. And also another person who played a very big role, it is Galliano Denardo at ICTP, Soon Swanberg at Lund University, Assel Green. But I have to say, if the network was really functioning, it was also thanks to the help of the government of Senegal, of the French embassy here, and of multiple governmental organizations all over Africa, because when we are organizing our meeting, it is in this country that we got a real strong support in order to realize all the things that we have done. So the activities are workshop, school, conference, development and cooperation in laser and optical science, training program for development and building capacity. This is one of the main purpose of a network. As you know, in Africa, it is extremely important to work on building capacity. And also we have activity in international society. Myself, I am a vice president of the International Commission of Optics, representing the LAM network, which is an international society like Optical Society of America, SPIA, IEEE, and ICO and other organizations dealing with optics at international level. This is the different representative in Africa. We have representation in all Africa, and also we have international contact. Even if there is somebody who wants to be one of our international contacts, it will be with a pleasure that we'll accept that. So this is some photo concerning some activities of the network. This was the ICO, the first ICO meeting in Africa, a topical meeting with the president of ICO, and which at this time he was from the United States of Africa. And we have done many workshops. And one of our workshops, our delegate have been at the presidential palace with the president of Senegal, who is the former president of Senegal, who is here, and I am here. And all the other people are our different delegates all over the continent, from Tunisia, from Morocco, from South Africa, from Nigeria, etc., etc. And this is the creation of the African Physical Society here in Senegal in 2010. And this is the bureau member of the African Physical Society. And here we have also created the African Optics and Photonics Society with a steering committee which is composed of all the international members of International Optical Society from US, from Japan, from France, also from ICTP. We have always a representation from ICTP. Okay. This is one of our workshops during the International Year of Light. Here we make a big celebration of the International Year of Light, and one of the topic was light to the people. You know, in Africa there is 600 million of children. They have no light in the night, so they cannot study. So the problem of light is extremely important. And what we do, we just take a solar electric lamp. We go in the countryside, in the remote area, and we make a distribution of this solar lamp at school and also in some houses. And even up to now, we are continuing this campaign. Okay, now I come to my talk concerning the laser, and I start with the electromagnetic spectrum. As you know, yesterday our friend from Pakistan also talk about that. But here there is some image. I just want to show as a former director of a nuclear institute to show. I want to show this part. You see, this is ionizing radiation, so you have to be very careful. Okay, most of lasers are working in the infrared and visible light, but lasers are extremely dangerous. I tell to my students, never look at the eyes of a laser with your eye, because this is extremely dangerous. So this is the electromagnetic spectrum in the world. And now, you know, this year is the 60th anniversary of the invention of laser. It was in 1960 by the American physicist Mann, who made the first ruby laser. It was in May, so in a few months this will be a 60th anniversary of the laser. And this was a very tremendous invention, because there is so many applications, not only in spectroscopy, there is so many medical applications, in surgery, in everything we can say now, we can see the laser operating. So this is the scheme of this kind of laser. There is a ruby rod with a flash lamp, which can make the so-called inversion population in the laser system, and the lasing come. Oh, it's here. Okay, this is the system. You know, the ruby laser is the oxide of aluminum, Al2O3, and inside there is a crystal of chromium 3R+, and this chromium 3R+ have absorption band, and the absorption band are in the blue and in the red. And what is interesting is that if we make excitation of this absorption band, there is a desexcitation, which is a non-radiative process, and which come on the metabolic state, and we make the so-called population inversion, because in the normal atomic system, the electrons are in the low energy state, but in the laser system, you have to push the electron in the upper state, so that when they come down, there is the emission of light, and this emission of light is a stimulated emission, which have been introduced by Einstein in 1917. So the laser is invented 43 years after the theory of Einstein on absorption of light by matter. So this is just to say that it is very important to know that fundamental science and applied science are in real very implicated. Sometimes in our country, particularly here in Senegal, they think that if you are a theoretician, you are not an important person. But theory and application are strongly related. And the case of the laser is a good example to show that. So, this is myself with Towns. Towns is one of the inventors of laser. Towns and two Russians, Basov and Prokoryov. I met him in China in 2005 during the meeting of the ICO meeting. As I told you, I am a vice president of ICO. I was so happy to meet him. And a few years after, he died. So I was lucky that it was able to see him. They got a Nobel Prize in 1964. Towns, Prokoryov, and Basov. But they didn't get the Nobel Prize for the laser, but for the maser. Maser, it is a microwave amplification for simulated radiation, simulated emission of radiation. And laser is light amplification. So now I will talk a few things about the diode laser absorption modulation and saturation spectroscopy. This is a very, very important thing because today, you know, the diode lasers are, everybody can get a diode laser. Even this small pointer, inside there is a diode laser. We can buy here in the market in Senegal a diode laser for 500 Senegalese franc. But there is all the spectrum of the diode laser. There is very powerful, there is very, very low. There is some kind of diode laser. If you put your hand on the radiation, you will lose your hand. There is some other where, okay, no problem, even the children can play with, but they have to be very careful not to see the laser. So this is some of the things that we got here in our laboratory. I will talk about it in the investigation of rubidium atom. And this is the diode laser, GARLIS diode lasers. So the diode lasers, they are very highly chromatic and tunable. This is very important if you want to do spectroscopy. It is important to have a tunable light source. They are not expensive, as I say right now, and they have low amplitude fluctuation, and they have a good frequency and amplitude modulation capability. And also there are excellent sources for investigating absorption spectra of atoms and molecules in near infrared, in infrared region, which coincide with most atomic and molecular transition. And we present the possibility which is offered by diode laser in atomic absorption, saturation, and wavelength modulation. Why is this topic? Because in our lab first, we are doing a lot of theoretical calculation on resonance state of atoms, and this resonance state of atom, most of them are excited by laser radiation or by synchrotron radiation. So our first attempt in a laser spectroscopy was how to apply the laser spectroscopy in atomic physics. So and as I say, we use this laser GARLIS. Okay, tuning characteristic. Okay, I'm not going to talk a lot about that. I want to show some experiment, the experimental scheme. I'll show you the photo of the experimental scheme. So you have a thermoelectric controller. I say that because there is many students here, just to show that it is possible to do spectroscopy without really spending a lot of money in the African context. I hear yesterday your system cost $1 million, but they are extremely important. But in our context here, we have to try little by little, and at the same time, you can do a very high scientific investigation with such kind of system. Here we have a thermoelectric controller, you have a diode laser, you have a function generator, you have a cell. This is the cell for. I am always. This is the cell to control where we want to calculate the concentration. You have a digital oscilloscope, a PC. We have an etalon, the Fabry-Perot etalon. All this system together cost about 30,000 euros. So with 30,000 euros, you can do a very good absorption spectroscopy and saturation spectroscopy. To do saturation spectroscopy, which means a Doppler-free system, because the atomic systems are always moving, so you cannot see some of the especially the hyperfine structure of atom if you don't make a Doppler-free saturation spectroscopy, which means that you have to reduce the velocity of atom by applying counter-propagating light, so that you stop the atoms and you can see their hyperfine structure with a very small system like that, And I think that this is a very important. This is also, you can do a modulation spectroscopy, and in the rubidium. Okay, this is the atomic property of the rubidium. I'm not going also to bore you with this property, but I just want to. This is the level. People who are doing atomic physics, they know that there is such kind of level. There is a hyperfine structure level and so on. And what is important is that we can get the absorption spectrum here, and also you can get the modulation spectrum. This is the modulation spectrum. And I didn't see the, I have also for the saturation, but maybe, okay, this is the saturation spectrum, this one, you know. This point out the hyperfine structure of the system. And at the same time, by measuring the width, you can measure the concentration. So this is a way also for environmental science. I will talk about that later. Okay. So now the other topic is the laser and lead-induced fluorescence spectroscopy. Since the operation of the first lasers in 1960, laser-induced fluorescence spectroscopy technique is used very widely in research for variety of analytical application. For interrogation of plasma in the industry, you can see all the pollution coming from the industry, and also for determination of cancerous tissue to fluorescence spectroscopy of single molecules. This is extremely important, single molecule, because now we have a laser system which can go to femtosecond and to attosecond, which is the time of interaction of molecular system. So you can catch the molecular system in its interaction if the reaction have to go there or there with this such kind of laser system which are operating at the attosecond system. So and the LEAF is very sensitive approach, and it is easy to implement, and it is well investigated, and it is non-invasive technique, and it is imperative for many environmental monitoring. This is the principle of the fluorescence emission. If you make excitation of the atomic system, you go to the upper level, and this upper level can decay by emitting light, which is called a fluorescence light. So the fluorescence light can have different property. You can have phosphorescence. You can have fluorescence, phosphorescence. It depends of the state, of the spin of the atomic system. So this is the principle. There is some intercrossing interaction. There is some other interaction which are going to be important, especially if you are doing a medical application of laser spectroscopy. Okay, and what we have done, it is the monitoring of the vegetation by the detection, by spectroscopic detection. You know, if you use the fluorescence spectrum in the vegetation, most of the vegetations have chlorophyll, and the chlorophyll is absorbing in the green and in the red. And by looking at this fluorescence spectrum, the different shoulder of the fluorescence spectrum, you can have information about the status of the vegetation in terms of lack of nutriment, lack of water, etc., etc. This is a very powerful technique, and it could be also a remote sensing technique to know the status of the vegetation in the earth. So I just show again some results. This is the absorption spectrum of the chlorophyll, because here the main purpose is how to see the chlorophyll and how to measure the ratio of the two shoulders of the chlorophyll in plant. This is the system that we have used with the helium neon laser, which is also not very expensive. I remember the helium neon laser we bought cost at this time 6,000 euros. It was a 5 milliwatt helium neon laser. Also, with of course we have the detection system and all the other things, but the main is this instrumentation, which is a very small, with an ocean optic instrumentation, and where we have a blue diode laser. At this time also, the blue diode laser was very expensive. It was about 2,000 euros. But now we can buy a blue diode laser for $100, even less. Even less if it is a pointer, but of course with a pointer we are not going to do a spectroscopy. But if you have a real system, the ones that I show in the beginning of my talk, it costs less than $100. So you can do a very good spectroscopy with such kind of system. And this, the spectrometer here, the spectrometer is connected to the computer, and there is a software in the computer which can show all the different things that you want to see. So here, this is the application we have done in a plant, and this analysis have been done by my student. I think Traoré is here, Mbaye, and other student, and also Ndao, Conte, etc., to get the property of laser-induced fluorescence in plant. What I was saying is that it is these two shoulders, you know, you have this one and you have this one. The ratio of these two give you an information on the status of the vegetation. And this is extremely important. We got a project with a friend from Ivory Coast. They have their huge plantation of palm tree. And one of the important nutrients in the palm tree is the phosphorus. So for the detection of phosphorus, they got an portable instrumentation where we can make a detection immediately. And before, they was obliged to take the soil, to send it in France, to wait for 2 months to get the result, and so on and so on. And with a laser fluorescence spectroscopy, you can get the immediate result. And we have, in our laboratory, we got another technique. Instead of making instead of making the comparison of these two, we can make such kind of diagram. With this diagram, you see immediately, and you can measure immediately the ratio of the green, the fluorescence at 690 and the fluorescence at 745. Okay, now another important thing is the application in medical application. Also fluorescence spectroscopy. What we do here, with a simple blue diode lasers and with a photosensitizer, you can detect the cancer cell. You can make a diagnostic of a cancer cell. So the first step is that our systems that I show now, which emit the blue light, you go to the cancer cell especially in the skin, and you can see the spectrum. The shoulder here is the presence of a cancer cell, because we have a photosensitizer which is staying on the cancer cell. So you can see the signature. And after for the therapy, you apply the red light. For the therapy, you apply the red light. The function of the red light is to induce singlet oxygen in the cancer cell. You know, now normally we are breathing triplet state oxygen, but the singlet oxygen is a poison. If you breathe singlet oxygen, you will die immediately. So what is important is that this singlet oxygen, the generation of this singlet oxygen by laser light, induce the killing of a cancer cell. Of course, some medical person will say, okay, be careful. They could be a mix with other healthy cells, so you have to be careful. Okay. I see my time is going. Okay, this is just so I will show rapidly some of the experiments that we have done at the hospital here. And another thing is the X-ray fluorescence spectroscopy. The hand you see here is the hand of Traoré, working with this machine. I think yesterday he got occasion to show it, and we use it in different applications. You know, usually people, they use a big system where you need a cooling system with a nitrogen azote, liquid nitrogen. And the problem here in Senegal, the liter of liquid nitrogen is 10,000 Senegalese francs. And with our budget, we cannot do that. So I try with the International Atomic Agency to try to get a portable system with an electrical cooling system, Peltier system. And with this system, it was possible to do a lot of works. And maybe yesterday Traoré talked about it in geology, in agriculture, by using machine learning, also this is also in agriculture for different variety of tea. Maybe we can do it with oil, etc. In Cameroon, our friend do with oil, with the determination of palm tree oil. You know, there is a campaign against palm tree oil. But indeed, it is the environmentalists which is making this campaign. But the palm tree oil is one of the best oil if you make a spectroscopic characterization. Okay, and now laser-induced breakdown spectroscopy. I go very, very fast. This is the instrumentation that we have in our lab, and we use it to make experiments. This is the principle of ellipse. You induce the plasma, and the plasma is emitting light, and after there is an analysis of this light. What is interesting is in one single shot. In one single shot, you can see a lot of things. I can show this here. You know, in the single shot, you see all the elemental composition. But after, you have to work on your spectrum, and to see here in Senegal, in Dakar, we see the mercury in the bedhan, and we see the stain in the Bay of Soumbédioune. So it is a very powerful, and the zirconium. You know, there is zirconium everywhere in Senegal. Even if you go to the Soumbédioune, you can see the zirconium with your laser system. Okay, this is an application in medicinal plant, which is also an important topic here in citronnelle. And this is a medical application in dental. I got a student from Morocco who is working at the Dental Institute. And she got her doctoral thesis by working on laser breakdown spectroscopy on dentine. This is some of the spectrum obtained during this work. And it was in collaboration with our medical friend, Bintou Catherine Gassama, Soukeitin, which means that laser spectroscopy is a pluridisciplinary system, so it is very important in the university if you want to make interaction with biologists, with geologists, with anything you want. Okay, here, if you want, I can stop here because my time is over.
I think in the interest of time, after this
yes.
wonderful presentation, I would recommend